Welcome to the story Return to the Moon, Apollo for a New Generation. In this video we're going to be looking at how man may return to living and working on the moon. Now, following the huge success of the Apollo landing missions between 1969 and 1972, attention turned to Earth-orbiting human spaceflight with the development of the Mir, the Space Shuttle, and the International Space Station. The idea of humans living and working on the moon by the 1980s was quietly forgotten. However, the discovery of water, well, more precisely ice, on the moon in the 1990s radically changed the practicability of a lunar settlement. The emergence of new space powers, including Europe, India and China, has led to a new space race to the moon. So in this video we're going to be looking at the current mission proposals to land on the moon, working towards a permanent lunar village. And we're very lucky to have one of Surrey's very own space experts, Craig Underwood, who's going to be taking us through this fascinating story. Now, this video and this talk was held at the University of Surrey in Guildford earlier in December. And it's part of a series of lectures which the IET Surrey volunteers have staged over now 20 years. This in fact is our 20th anniversary of Christmas lectures, where we aim to inspire the next generation of students and school children to become engineers and take that up as a profession. We've worked in partnership with the University of Surrey for most of that time, and they've been very helpful in providing us with venues, and this time we had one of their PhD students, Chris, who came along to explain more about what life is like on the campus at the University of Surrey in Guildford and what student life is all about. So that was a very interesting topic, and I encourage you, if you're interested to learn about studying at university, to consider the University of Guildford. Now, for this talk, Professor Craig Underwood actually is an alumni of the university, so a very own local expert, but one who's internationally renowned and known for holding many qualifications in this field. And he was inspired by the moon landings between 1969 and 1972 and achieved a BSc degree in physics at the University of York. After being awarded a postgraduate certificate in education in 1983, he taught at Scarborough Sixth Form College and developed activities in satellites and wrote Satellites in Education, A Guide for Teachers, and I quizzed Craig more about that towards the end of the questions and answers that you'll see later. On moving to the University of Surrey in 1986, Craig was Research Fellow responsible for creation and maintenance of software for the UOSat Satellite Control Ground Station. And that was a groundbreaking project in microsatellites. Within 2 years he became senior engineer with Surrey Satellite Technology Limited, where he was responsible for mission analysis and thermal design of the UOSat spacecraft. 1990 saw Craig become Surrey's principal investigator of space radiation environment and effects, and in 1996 he was awarded a PhD degree from the university. He's led the Environments and Instrumentation Group in the University of Surrey's Surrey Space Centre, pioneered with the UK's nanosatellite activities as Chief Architect of SNAP-1, amongst many other projects. He's now the Emeritus Professor of Spacecraft Engineering with the Surrey Space Centre here in Guildford, and he was very kind in coming to talk to us about the journey back to the moon. So over to Craig.
So, welcome everyone. It's my pleasure to present to you this talk on Return to the Moon, Apollo for a New Generation. As was just said there, I had the pleasure of having 36 years working in space. It wasn't something that I thought I would ever do. I was read out there. I did this degree in physics, computer science, and then I did my teacher training and taught in a sixth form college. Just as I was doing that, University of Surrey were launching its first satellites. And so I got involved in tracking those because I could program. I could get a BBC micro, for those who remember those days, to actually decode the data coming from the satellites. So I came down to work in the ground station. In fact, that picture there shows me in 1986 there with the venerable PET computer, but everything else was pretty much hand built. And although I'm formally retired, I still teach about space. So it was very interesting to hear Chris saying how he's been inspired by companies like SpaceX today. And I think that really is the theme of today's talk, is that space is very inspirational to people. And I count myself very lucky to have grown up in the 1960s when the pace of technological change was enormous and everything seemed to be very exciting. We had Concorde in this country, and interestingly, I think Neil Armstrong said that Concorde was more difficult to achieve than the Apollo missions. So it shows us the level of technical achievement there. And of course, I grew up with the fantastic television series from Jerry Anderson and so on. So it was all very exciting. Kennedy captured that spirit, I think, when he said, the eyes of the world now look out to space, to the moon and the planets beyond. And certainly space and space technology has been really important in terms of for inspiration. In fact, it was 1961, May 1961, that Kennedy gave his speech to Congress that the US should commit itself to achieving the goal before the decade is out, he said, of landing on the moon and returning him safely to the Earth. That was an astonishing thing to say when, at that time, the only people who had got anybody into space was the Soviet Union, with Yuri Gagarin, just 6 weeks earlier. So from zero start, Kennedy was saying that within 10 years, they would have an American on the moon. And a year later, so he gave a famous speech at Rice University, where he said, "We choose to go to the moon." I had to repeat it because of the applause. And he said, not because it's easy, but because it is hard. And that probably a serious underestimate of what was needed. But it certainly kicked off the space race. And the 1960s into the 70s was characterized by that really technological race between two philosophical ways of running the world, either Western capitalist democracy, represented by the United States, or Soviet communism, represented by the USSR. And it really was a race. And in fact, in the early years, through to the mid-60s, certainly, the Russians were well ahead of the US. It took a time to catch up. But it was indeed the Americans who got to the moon first. So Kennedy's challenge was met, of course, at about 8:17 Universal Time, July the 20th, 1969, when Neil Armstrong stepped onto the moon. And of course, Buzz Aldrin, Edwin Aldrin, was with him in the lunar module. An amazing achievement. If you listen to the talk over the radio as they're coming in to land, if you have a technical background, you realize just how close we were to disaster, because just as the craft was coming down to land, the computer malfunctioned. And a very young engineer was able to make the right call, which is that they should carry on and actually land. In fact, they overshot the proposed landing site and had to, Neil had to manually land the craft, looking for a new site to land on. It wasn't at all easy. But after that, there were 6 Apollo missions that followed, Apollos 12 to 17. The latter missions up to Apollo 20 were in fact cancelled. And of course, of those, only Apollo 13 didn't land on the moon because of the famous disaster that happened to Apollo 13. Again, we were extremely fortunate, a fantastic feat of engineering to get them back alive. But in that period, from 1969 to 1972, 12 astronauts walked on the moon, and they spent a total of 12 and a half days actually on the moon. So it was a long time. They explored 6 sites of scientific interest. And indeed, the knowledge and the material that they brought back revolutionized our knowledge of the Earth-Moon system. One of the things it told us, for example, is that the moon was created in a most enormous collision early on in the history of the Earth, when something about the size of Mars impacted on the Earth and caused the moon to sort of splash out into space and form our satellite. Indeed, without that, it may be questionable whether life could have continued to exist on the Earth. And it turned out the moon was a Rosetta Stone for planetary science, because from dating the rocks and material that we got back from the moon, looking at the cratering record on the moon, we were able then to look at other planetary surfaces, and from the craters and crater counting, actually work out how old those surfaces were as well. So there was a scientific benefit to all of this. But perhaps the long-lasting legacy of the moon shots was pictures like this, a famous picture taken from Apollo 8, looking back at Earth, the so-called Earthrise picture. It really showed people for the first time that, yes, we really do live on this tiny little blue marble, beautifully there, lit against the black velvet of space. And it showed us that, you know, the world is a very small place and we all share it together. So I think that made a profound change in people's outlook about the Earth. So the question was really, why did the US stop? Because it looked, I mean, everything went very well with the Apollo program, remarkably, actually, bearing in mind how risky and how absolutely pushing the state of the art it was. Well, of course, there were other things happening in the 1960s. There was civil unrest. There was the Vietnam War in America, for example. And really, although the engineering was astonishing, literally out of this world, and the science was important, the real reason to go to the moon was really a political one. It was to show what Western science could do in comparison with communist Russian science. So there was also, of course, public unrest. Indeed, Kennedy had a lot of difficulty persuading Congress to support the program in the first place, because, of course, it was very expensive. It cost something like $25.4 billion in 1973 dollars, which is a huge amount of money. It sounds a huge amount of money. And people say, well, you're wasting money spending all this money in space. But of course, the money isn't spent in space. The money is actually spent on the ground. It's people's jobs, etc., that are involved. And something like 400,000 people were involved over that period of time. 20,000 industrial firms and universities were involved. And indeed, all of our modern lifestyles absolutely hinge upon the technologies and the techniques that were developed during that program. Without that program, there wouldn't be a Silicon Valley. We probably wouldn't have integrated circuits in the way that we have today. And the internet generation that we've raised today wouldn't have had the internet without that investment. So it was a brilliant program. Of course, ironically, by the time the moon landings were taking place, we had a different president. We had President Nixon. Nixon had already committed NASA to the Space Shuttle. And so really the focus shifted to that, what turned out to be an extremely expensive program of getting the shuttle to work. And the Russians basically gave up in 1976. They moved on to space stations and more Earth-focused work. That's not to say that the Russians didn't have a good go at going to the moon. They developed an enormous rocket, the Enron rocket, which was the same size as the Saturn V. Indeed, you need a rocket of that size to get all the way to the moon. And just to give you a scale, if I can leave off camera for a minute, to scale, here's the Earth, my nice little beach ball there. And then if I walk over here, this is a scale distance to the moon for the Earth of that size. There's the moon, again, to scale size. So it's a long way away. You need a big rocket to get there. They also developed landing craft and sort of the craft to carry the crew out there. So very similar in concept to the way the Americans did it using Russian technology. Although, unfortunately, the Enron rocket wasn't successful. They tried to launch it 4 times and unfortunately it exploded each time. There was a lot of success out of the Russian program. In particular, they produced the first automated sample return with Luna 16 in 1970. And they also produced the first mobile robot on the moon with Lunar Hot 1, which operated for nearly a year between 1970 and 1971. You see the craft in the pictures there, and also TV pictures taken by it of its landing point. So Lunar Hot 1 was extremely successful. It took something like 20,000 TV images. And to last a year on the moon is not easy because the moon is a planet, it's an object of extremes. In the lunar daytime, it's incredibly hot because there's nothing to protect you from the blast of the sun's rays. About 1.4 kilowatts per meter squared of heat coming off the sun. But in the lunar night, it is absolutely freezing cold. There's nothing between you and cold black space sitting at minus 270 degrees. So it's an object of extremes, and the craft had to survive that. Lunar Cod 2 in 1973 lasted 4 months. It also did very well, returning about 80,000 TV pictures. And Lunar 3 would have been carried in 1977, but unfortunately, the program had been cancelled by then. So now you can see it in the museum in Moscow. To give you a comparison, though, the Apollo astronauts were able to drive with their lunar rover some 90 kilometers on the moon on the latter Apollos. So 1976 was the crucial year then, when these programs really came to a halt. And those of us who were around then will remember it was that long, hot summer that seemed to go on forever. Great drought, of course, as well. And in fact, that was the year that the Russians landed on the moon with Luna 24. And that also returned a sample of material. 170 grams were returned by that particular craft. Now, nothing went back to the lunar surface until 2013. So for a long time, the moon was an unvisited object, that lonely satellite up in the sky. To give you a comparison, by the way, in total, the Russians managed to get 300 grams of material by automatic probes. The Apollo astronauts brought back 382 kilograms of material by collecting. And the latter Apollos were characterized by astronauts who were geologists. So Harrison Schmitt, particularly, he was a trained geologist. He knew what to look for. And famously, he saw the orange soil, which surprised everybody on the moon. Some very important material was brought back. Surprisingly, you can see that sample at the bottom there, sample 14321.46. That contains a little piece of rock. That is Earth rock. And that Earth rock is the oldest rock we've ever detected on Earth. It's about 4 billion years old. It's the oldest sample of Earth that we've seen. And we didn't find it on Earth, we found it on the moon. It's material that had been splashed out onto the lunar surface. So what that showed us is that humans could do very well. And indeed, it's part of the drive that we want to go back to the moon because, to be honest, although robots are great, humans are better. Now, the mid-70s and 90s then, our focus shifted elsewhere, more towards applications of satellites. Remote sensing became a thing with Landsat in 1972. The development of the shuttle, of course, so lots of actions in Earth orbit. And with the Russians, Salyut and the Mir space stations, and of course the great deep space missions, Viking, for example, the missions to land on Mars, and of course Voyager. I have to say Voyager is my favorite robotic space mission. And indeed, it was that era that Surrey started its activity. And Professor Sir Martin Sweeting, who was a student here in the Department of Electronic Electrical Engineering, formed the University of Surrey Satellite Project, the USAT program, and designed and built these small satellites. They're about the size of a microwave oven. And the first two, USAT 1 and USAT 2, launched in 1981 and 84, respectively, were launched for us for free by NASA, for which we're very grateful. And they pioneered this idea of low-cost access to space, and we then formed a research organization to market that technology to the world, and with great success. Ironically, the mission that refocused attention on the moon wasn't going to the moon. It was Galileo. Galileo was a probe destined to go to Jupiter, but it did so in a rather convoluted way. It turned out, unlike with the Voyager probes, which went straight out from Earth to Jupiter, the quicker way to get there is in fact to go to Venus. So Galileo left Earth, went to Venus, used the gravity of Venus to accelerate, came back to Earth again, used Earth's gravity to accelerate again, about a year later came back to Earth and finally used another bit of Earth's gravity to accelerate even faster and got it out to Jupiter. So while it was doing all that, of course, it was in the presence of the Earth-Moon system and was able to use its sensors to look at the Earth-Moon system almost as if we'd sent a space probe there for the first time. And we saw those sort of blue marble shots from the new generation of cameras that had. So just to give you the difference between 1969 and 1992, this is a TV camera as flown on the moonshots, the Apollo moonshots. It's a Vidicon tube, so based on evacuated tube technology, and very mechanical and very heavy. Galileo carried electronic solid state camera, what was called a CCD. This is a CCD of that vintage, 1990. And there's the imaging chip, and that was at the focus of a telescope like that. And that was able to return much, much better pictures using much smaller, lighter technology. So Galileo was a revelation, because as it flew by the Earth-Moon system, and I love this little movie shot there, you see the Earth and the Moon half lit by the sun there. It's almost like looking at a distant planet. It was able to use its multispectral camera to look at the surface of the Moon, and because we can look at it in different color bands, we can get much more detail about what the surface is actually made from. We're able to see the different surfaces. The reds and the pinks there are essentially basalt of the volcanic or igneous rock that's come out. The blue there, which is in fact the Sea of Tranquility where Apollo 11 landed, that is indicative of large amounts of titanium present in the lunar regolith. We call the surface of the Moon the regolith. And the reddish, pinkish areas are more iron rich. And the light blue areas, that's new material. So that's from relatively recent impacts on the lunar surface. And of course, I'm talking over geological time here. So recent is still billions of years ago. Although some of them actually are only millions of years old. So we're all familiar looking at the Moon. In fact, the Moon's beautiful in the night sky tonight. We only, of course, ever see one side of the Moon because it's in what we call harmonic capture with the Earth, so we only ever see one side. But you can see with the multispectral camera there how much more detail is visible to our instruments than is visible to the human eye. Now, of course, in passing by the Moon, we get to see parts of the lunar surface that we never see from Earth. And in particular, this shows the rear side of the Moon, which we can't see from Earth, but we can see with our robotic spacecraft flybys. And the ringed area in red there is the South Polar region of the Moon. And it shows an area known as the South Pole Aitken Basin. It's a very deep area of the Moon. And there are craters there that are in deep shadow. And we believe that the sun has never shone on the base of those craters. And because of that, they are astonishingly cold. So the sun has never shone on them for billions of years. And there's just the possibility that water, which was delivered to the Moon by cometary impacts, could have condensed there and formed ice. And so that gave us a sort of scientific endeavor to go and see, is there ice at the poles of the Moon? So the first probe really to look at that was Clementine. Clementine was put together as an example of a sort of low-cost approach to space, or at least by American standards, a low-cost approach to space. It carried some extremely good sensors, multispectral sensors looking across ultraviolet, visible radiation, near-infrared and thermal infrared. It also carried a LiDAR, a laser radar, so it could measure the topography of the Moon. And using this combination of instruments, it was able to get us great data on the form of the Moon and also the surfaces, etc. So in 71 days of orbit around the Moon, it imaged the entire lunar surface. It took over 1 million pictures of the Moon, and some of those in high resolution as well. And it was then due to actually leave the Moon and go off to visit an asteroid, but sadly there was a fault on the rocket and it wasn't able to do that. But this is the topography map of the Moon. It's stripy because it's been painted by a laser. And what you're doing is firing a pulse of light down to the surface, timing the time it takes to go down and come back again, reflect back again. And from that, of course, you get the height of the lunar surface. And we see there again, ringed in red, that purple area, that's the Aitken Basin. It's quite deep. In fact, the darker pinky blue areas are quite deep. And then you've got the highlands as well on there. Now, when you look at the Moon, you see the sort of dark patterns of these basins, the mare as we call them. And then you've got the brighter areas, which are the highlands. So they're sort of familiar. But we don't get to see the poles very well from Earth at all. And looking down over the poles, this is the South Pole and the North Pole, you see how shadowed some of the craters are in those polar regions. So that gave us some impression that there might be ice there. And of course, with its multispectral camera, it could also map materials. So again, looking at titanium type minerals and iron type minerals. And so we're getting a lot of data on what is actually there. They did an experiment with radio. Now, when you send a beam of microwaves, in fact, very similar to your microwave oven frequency, in fact, when you send that to the lunar surface and it scatters off, it's possible to pick that up from Earth. This is called a bistatic technique because you're transmitting from the spacecraft, but you're receiving the ground from stations like the Arecibo station in not Arecibo, sorry, the Goldstone station. And it turns out that the nature of the regolith affects the radio wave. So if it's rock is a good insulator, it doesn't reflect very well. But if it's ice is actually conductive slightly, and it reflects much better. It also changes the polarization of the radio wave. And indeed, they got a signature that was indicative of ice being present. Sadly, they did further experiments where they got the same signature from other areas of the moon where we're pretty confident there can't be ice. So it was slightly inconclusive, but it may be just a hint that there was something there. A few years later, Lunar Prospector was launched, again, relatively small satellite that also carried multiple instruments, but no cameras this time. It carried other scientific instruments, gamma ray spectrometer, neutron spectrometer, an alpha particle detector. What it was looking at is the effect of cosmic rays hitting the lunar surface, and then the effects of radioactivity in the lunar surface, but also the splash you get of subatomic particles coming off those cosmic ray hits. In fact, looking at neutrons coming back. And also they carried very sensitive magnetometers to measure the magnetic field. And also they did radio experiments to measure the gravity of the moon. Now these maps here show the presence, we believe, of water. You notice the polar regions there showing up as purple. That's done by looking at the neutrons coming back. So when a cosmic ray, which pretty much is mainly protons, and the rest of it is pretty much alpha particles, when a proton crashes into an atom, it will sometimes hit the nucleus and splash the nucleus apart. It will just tear it apart. So what comes out are protons and neutrons. Neutrons are very difficult to stop because they have no electrical charge. They sort of move through matter really, really easily. But what will stop them is a hydrogen nucleus, a proton, because it has the same mass as a neutron. So when they collide, a lot of energy is removed from the neutron. So what you find is that if those neutrons have passed through something with lots of hydrogen in it, the energy is much lower. And that was the signature that we were looking for. And ask yourself, what kind of material has got a lot of hydrogen in it? The answer is water, H2O, after all. So we believe that that is indicative of ice. It also found thorium. Thorium is an interesting material. It is a potential fuel for nuclear reactors that we might put on the moon, or indeed we could fuel Earth nuclear reactors with thorium. It's rather safer and cleaner than uranium and plutonium. And it also showed us the weak magnetic field of the moon. It doesn't have a liquid core like the Earth does, so it doesn't have a dipole field with a strong dynamo. It just has basically a remnant magnetic field in the crust. But it also showed us these mass concentrations. The map that shows the red dots there, they are concentrations of matter underneath the basins of the moon, and it's to do with the way those basins formed. And they are, I have to say, a pain to putting something in orbit around the moon, because the gravity field is extraordinarily complicated. And it means that no orbit, or very few orbits, are actually stable around the moon. If you put a craft in low lunar orbit, eventually it's going to crash onto the lunar surface because of these tugs from these mass cons, as they're called. And to end the mission, they deliberately crashed the probe onto the lunar regolith, and they crashed it into a shadow crater just to see if we could see a plume come up and spectroscopically see if there was any water in that plume. It duly crashed in the right place, but we didn't see any plume at all, unfortunately, so we have no idea if there's anything there. So that's the American effort. Of course, in 1975, the European Space Agency was formed, and throughout the 1970s, there was the development of the Ariane rocket. And so we started a European space program. And the first European mission to the moon was Smart 1, which was launched in 2003. Smart 1 used an ion engine to get out to the moon. Sounds a bit science fiction-like, but in fact, ion engines are well tried in space. The thing about an ion engine is it's a really effective way of using propellant. The downside to an ion engine is the thrust is tiny. So rather than blast off and go to the moon within 2 or 3 days, as we can do with a chemical rocket, it took over a year to get there. You basically have to very slowly accelerate and spiral out over the course of a year. But it did that, and it got into the presence of the moon and took pictures. It also looked at those polar regions, confirmed those shadow regions, etc. And the technology was later used on Philae, the lander that landed on the comet. So Smart 1 was also crashed onto the lunar surface. You see the bright light there, the top picture, that's the flash caused by that hypervelocity impact. But again, sadly, we didn't see anything. We didn't see any plume or any ice. Now, Japan also sent missions to the moon. Their first probe was Mrs. A, otherwise known as Haitan. Haitan was the first probe, actually, to go back to the moon after Lunar 24 in 1976. And it was very successful. It again carried various cameras and was followed in 2007 by a second probe called Selene, which carried a high-definition TV camera. And if you look at the videos from that, it's just astounding. It's like you're really floating above the lunar surface and moving over the top of it. They're beautiful pictures. But again, it returned useful data, including showing us that actually Earth's oxygen is ending up on the moon. The Earth is losing its oxygen slowly, so we don't have to worry too much, but we are losing our atmosphere slowly to space, and some of that is ending up at the moon. The big thing that's changed in the 21st century, though, is the shift from the Western powers to the Asian powers. And the two prime Asian powers, of course, are India and China. Both India and China have extensive space program, both with intentions to have manned flight. In the case of China, they already have that, space stations and so on. And the Chinese have done really well with a well-programmed stage program of getting to the moon. They did also the spacewalks, which we did in the West and in Russia. They too have got a phased program like Apollo, going for orbital missions first of all, then soft landers, then sample return, and then finally humans on the moon. And they've had great success. Chang'e 1 was an orbiter, worked brilliantly, mapped the moon in various ways. Chang'e 2 was also very successful. Its instruments were a little bit better. And indeed, it left lunar orbit and went off to an asteroid. It went to see asteroid Tutatis and did extremely well there. So that was a fantastic mission, complex mission. Chang'e 3 landed on the moon, and it deployed a little rover called U2, little tiny robotic rover, and that was also successful. It did suffer a mechanical breakdown after a while, but then, as I've explained, the lunar environment is really hostile. It's not easy to make something last there. The lander used a radioisotope heating unit to try and keep warm in the lunar night. Chang'e 4 repeated that success, but landed on the far side of the moon, so out of radio communication with the Earth. You can't communicate to the Earth if this is basically the moon between you and the Earth. So, of course, it had to use an orbiting satellite as a radio relay to relay information. And in fact, NASA will use that Chinese satellite as a radio relay for later missions, Artemis missions. But Chang'e 4 was a great success, and indeed Chang'e 5 was also a great success, landing this time and returning samples. They returned 1.7 kilograms of rock, totally robotically. First time that had been done since the Russians finished doing that with Lunar 24 in 1976. So they're well on their way to having Chinese taikonauts, as they call them, on the moon in the next few years, certainly by 2030, I would say. Now, India has also gone to the moon. They had great success with Chandrayaan-1, which managed to map. And actually, Chandrayaan-1 really has produced the best evidence we have for ice present at the moon with its various instruments. And so we are pretty confident there is water there, but not on the surface. It's just slightly under the surface of the rock. Chandrayaan-2 also was due to land, but sadly it crashed on the moon. And Chandrayaan-3 is due for launch next year. So fingers crossed they'll have more success with that mission. But the Indians have done very well as well. So with all this international effort going back to the moon, this is the Americans to to think about it again. They launched a mission called Lunar Reconnaissance Observer that looked to the moon in various ways and got us great data. But one nice thing about it is it carried very high resolution cameras, and we can see the Apollo hardware on the moon. So for those skeptics who say you never went there, these are the images that show you they're still sitting there. You can see the lunar module there on the ground surface. You could even see the tracks left by astronauts and also by the lunar rovers as well on the lunar surface. So all of them are there, casting their shadows. It's still there. We believe the flags, by the way, are probably bleached to white by now, but everything else is there. And there you see again the sort of Earthrise seen by this spacecraft. And that spacecraft is still working, so hopefully we'll get more data from it. L-CROSS was a mission to, again, try to see if we could get a plume of material that we could analyze. So an upper stage of a rocket was blasted into the lunar regolith. We saw the flash of the impact, but again, sadly, nothing in terms of plume of ice. Well, maybe just a hint of spectral lines. So maybe there's a few percent by mass of water there. Clementine was another small mission that went off to the moon. This combination of spacecraft really has paved the way for human exploration, really, of the moon. I'll explain some of the problems around the moon. These mass cons, the GRACE mission there, mapped them extremely accurately. They are a pain. It makes the orbit predictions very difficult to do. It is possible to do them, but it's much harder than orbits around the Earth. And something the astronauts saw, and they sketched, this is actually a page from the astronauts' notepads. They saw these strange lights in the sky, which were almost certainly dust plumes coming up electrostatically, we believe, from the lunar surface. So LADEE was a mission to go and investigate that dust. There is a sort of transport of material into space from the moon. So then we get into the plans to go back to the moon, and that started in the early 2000s. It was obviously a follow-on from Space Shuttle. Amazingly, rather than pursue the Space Shuttle technique of having a reusable orbiter part, we really went back to Apollo, which is basically using a big rocket, this time with solid rocket boosters. So their vision for space looked to getting back to the moon by 2020. You probably have noticed that we haven't got back to the moon by 2020. So the Ares rockets were really Apollo on steroids, a much bigger rocket, actually, much more powerful. But when President Obama was elected, he cancelled all these projects. So they effectively killed it off. And there was a public outcry. And the engineers, the public, NASA, all decried the fact that these programs had been cancelled. And so, in fact, they were reinstated under a slightly different name. And today, the Ares vehicle is known as the SLS, the Space Launch System. And that's what blasted off the other day. So SLS is the way that NASA is going back to the moon and also potentially go on to Mars. It's interesting to see that it's taken over 10 years for that rocket to come to operation, with a launch on the 16th of November this year. Its cost has exceeded $14 billion. And by contrast, the Saturn V took 6 years to develop from no knowledge at all to actually getting to the moon in just 6 years. So it shows you the scale of the achievement in the 1960s. So the aim of Artemis, the program, is to have the first woman on the moon and the first person of color on the moon. And ideally by 2024, I think probably 2025 will be the earliest that they do that. The craft, called Orion, is like a sort of souped up version of the Apollo command module. It can carry twice as many people, 6 people. And it will get to the moon by means of something called the Lunar Gateway. This is like a space station in orbit around the moon. So if you like, we'll go from the Earth, rendezvous and dock with this space station in lunar orbit. We'll then go down from the space station to the lunar surface, come up from the lunar surface to the space station, and then come back to Earth. So you can imagine this traffic going backwards and forwards between Earth and the Lunar Gateway, and then operations down to the lunar surface. So tests were done, and the plans were made, again, a staged plan, getting orbits and then eventually people onto the moon, really following the Apollo game plan, actually. So similar to Apollo 8, which is just being done right now, and missions similar to Apollo 10 and Apollo 11, getting a person to the moon. And this is the current mission, Artemis 1, which was launched just a couple of weeks ago. It's on its way back to Earth now. It should come back to Earth this weekend. So fingers crossed for that. It went to the moon. It passed the moon. It deployed 10 very tiny spacecraft called CubeSats to do some science. But it went way beyond the moon in order to demonstrate deep space operations, and then is on its way back. It has that typical figure-of-8 trajectory. So that will splash down, all being well, this weekend. And here are some pictures from it. You can see there, it's a sort of a selfie. You see the craft itself with the moon in the background there, a picture of Earth taken from quite considerable distance away, and one of the CubeSats deployed as well. So it's worked very well, I have to say. It's very pleasing to see that. And if Artemis 1 is completely successful, which I'm sure it will be, it will lead to Artemis 2 in 2024. Artemis 2 will be the first time people are put on this rocket. And then if that's successful, with Artemis 4, we'll put people back onto the moon. There's Gateway. It's obviously driven by NASA, but it's not just NASA. JAXA, the Japanese Space Agency, ESA, the European Space Agency, are all involved. And even the Russians as well, although that may be tricky at the moment. But essentially the people involved in the ISS, the International Space Station, are contributing towards this. So it'll be a big thing in lunar orbit, a sort of way station to the moon. Now, as well as NASA programs, the government programs, there's a lot of work now with private enterprise. And so NASA announced various competitions for people to look at, providing a service, the sort of Amazon delivery service to the lunar surface, be able to move material, freight, people backwards and forwards to the moon. Various people bidded into that system and come up with different concepts. And I'm sure that in very near future, we'll have a private spacecraft land on the moon, not just a government-sponsored one. Indeed, Russia is planning to go back to the moon as well. They finished with Luna 24, so Luna 25 to 28 are the proposed missions, maybe starting with Luna 25 in July next year, fingers crossed. And they will be essentially, again, paving the way to putting people back onto the moon, but this time Russians back onto the moon. And it could well be that private enterprise gets there first. I wouldn't like to place my money on whether NASA or Elon Musk with SpaceX gets there first, or indeed Jeff Bezos with Blue Origin gets there first. There will be a kind of race to the moon with private enterprise as well as government institutions. And so the world of space has really changed in the 21st century from something that only governments can afford to something that private enterprise is really pioneering. And I have to say the kind of spirit of these private enterprise companies is very like the spirit of Apollo, is really going for it and making rapid progress. And even our own company here in Guildford, Surrey Satellite Technology Limited, have recently announced that they are going to provide a commercial service, a kind of navigation communication relay service around the moon, and working in close collaboration with Goonhilly, which was in fact the first station that received signals from the first communication satellite Telstar back in the 1960s. So Goonhilly has this enormous dish antenna, very suitable for communications into deep space, including at the moon there. So Surrey is working very closely on that. And it's a possibility that SSTO will carry a Surrey Space Centre CubeSat mission to the moon, but we'll see how things go on that one. So why should we go back? Well, there's, of course, the adventure, there's the science, but actually there's the hard-headed business. The moon is full of very, very useful material. And there is this whole plan to start to mine these materials. We're going to run out of critical metals, for example, very soon. If we all want to drive electric cars, where's the lithium going to come from? Where are all the materials that we're going to need to run our green economy going to come from? There's not enough material on the Earth, but the moon could be a supply of that. And so ISRU, as it's called, in situ resource utilization, is looking at how we might use lunar material to build a permanent base there and to start to use some of that material. And there's volatile material there as well. We can make propellants for rockets. We can then use the moon, as we always dreamed, as a staging post to exploration of the whole solar system. So it's much easier to send someone to the moon and then send them on to Mars than it is to send them to Mars straight from the Earth. Indeed, we might even be able to send people further out into space, perhaps to the asteroid belt or maybe even beyond. So a lot of research is going on right now on how to use 3D printing using lunar regolith. That's already been done. So we can print structures using 3D printing techniques with the material that we have on the lunar surface. And habitation, keeping people protected from the extreme environment of the moon, keeping them protected, of course, from cosmic rays. But, you know, it might involve burying habitats or inflatable habitats, as we see here. And indeed, if we look at the designs of lunar bases over the years, I start with Jerry Anderson's UFO base in 1970 there. Of course, this has been studied since the 1970s. Indeed, my generation thought we'd be definitely living on the moon by the 1980s, and it never came to pass. But maybe it will now for this generation. So I would confidently predict by the mid-2030s, 50 years later than we hoped, our young people will be living and working on the moon. And some people may be living their entire lives off planet, off Earth, as it were. So Apollo was the project that inspired my generation. I'm sure it made many people study scientific topics at school and become engineers or become scientists. Certainly it was the case in my case. Artemis, I think, is something that will inspire our new generation to look out to the moon. And it will be an international endeavor. It won't be now just Americans or just Russians. It'll be the whole world going out into space.